Greetings. My name is Lindelweyizizwe Manqele. I'm a lecturer at University of Limpopo, South Africa. My talk today will be about the impact of big data and decision-making in IoT applications, especially in the context of Africa. So we're gonna use this diagram that was designed by Coetzee in 2019 to illustrate the whole context of my talk. So you're gonna see this diagram more often. So we decided to start by defining what Internet of Things is to those that may not understand. So by Internet of Things, we are referring to the interconnected objects, not just any object, but objects that are able to sense and actuate. So these objects, they need to have a form of an infrastructure where they can have a connection or communication. So that speaks to the internetworking, right? So after being connected, and then it goes to this stage number 3, which is the process. This process utilizes the standards and the protocols and other existing technologies to make sure that the data that is being streamed from these sensors, communicated through the well-established infrastructure, can be passed through using certain processes and then deliver a service at the end of the day that can be used by people or the society. Right. So in the context of IoT architecture, when we talk about the interconnected devices, we are talking about a resource that can help us to produce more and more of big data, right? So remember that the talk is about the impact of big data. So before we even make those decisions, we need lots and lots of data. So this component helps us to generate more data. As I said, that the communication we're speaking to are more advanced technologies that exist, like 5G and 6G. There's a lot of research that is taking place in the space of 6G. Then we're going to utilize that to make sure that there is a reliability, right? So now when we have streamed this data from the sensors, communicated it, then we can use this data for different purposes like the analytics, decision-making, predictions, and all that. Now I decided in this slide to make an example of what are those potential use case scenarios that can be used to deliver a service. It can be waste collection, it can be e-health, it can be water distribution, it can be agriculture. But in this context, we're gonna look at 2 of these use cases. You're gonna find out as I continue to do the presentation. And then at the end of the day, then we're going to have what we call a smart society or a better environment, depending on the use case that we are using this architecture for. Right. So the data that we seems to be a drive for the whole architecture is divided into 3 categories. We have what we call the data in motion. This is the kind of data that some people call it real-time data. This data, it can be used for services that are needed now. We stream data now and we deliver those services now. And we have data as a service. These are the kind of data that, even though there could be a delay, but it's nearly real time, really, because we can go to Twitter where we can see what is trending. We can even have those financial models that can inform us of what is expected and what are the functionalities within the finances that are put in place. And then we've got the data at rest. The data at rest is the data that can be found on a device, can be stored. It was stored a long time ago and it can be used, can still be very relevant for big data and decision making because it can be used for other potential services, right? So as I said that there was a list of potential use cases that I mentioned before. So one of the potential use case that we're going to look at is the waste collection. The waste collection in this case, because we said we need to have objects that are interconnected and are able to sense. So those objects in this case are smart bins. So we need to have smart bins that can tell us whether the bin is full or empty or half, right? So because this is the project for the city of Johannesburg, there is a city of Johannesburg report 2040 that outlines most of tasks that needs to be completed or that needs to be done. So one of those task in a report is to make sure that there is an effective waste collection method. So we are just taking that use case and we are using it in a city of Tshwane, which is Pretoria, also known as Pretoria. So by this communication, we are assume that we have smart bins in place, and then we can utilize the Tshwane Wi-Fi that is available in other places, even though it's not available in all places as yet, but majority of places in Pretoria can access the Tshwane Wi-Fi. So in this case, what happens is we are able to visualize, to see how many bins that are full, how many bins that have, how many bins that are empty. But visualizing or seeing those bins doesn't mean that we know what to do. That's why we need effective decision-making technologies or methods in place that can help us to make sure that we make right decisions such that we do not struggle, we do not have a problem of cost and otherwise, right? So at the end of the day, how will the society benefit from this kind of use case? They will benefit because they are going to have a clean environment, and that will help them to have less diseases such as TB and all that. So they'll have a clean environment that they can utilize because of this model that will be in place, right? And then again, we have another use case that is called the water distribution. This one, it utilizes their water infrastructure. So what we need in this use case actually was also motivated by a certain journal that was produced by Louis in 2005 and other team from UCT and CSIR. So they were looking at the particular use cases or potential projects that they can address in terms of a smart city. So one of them is the problem of water scarcity. Water scarcity is not a problem of South Africans only, but other African countries also experience that. But in the context of South Africa, how can we address this problem of water scarcity using the IoT? Now, we cannot make the rainfall with IoT, but the only thing that we can do is make sure that we have good resource allocation methods that are in place to make sure that this water that we have, we share it equally. By equally, we do not say everybody must get 10 liters, but we are saying by just looking at the amount of demand per household, then we can meet them 50%. 50% of household number one can be 10 liters. 50% of household number two can be 20 liters. 50% of house number three can be 50 liters and so forth. So in this case, that's where the multi-objective methods come in, where we want to make sure that we allocate all these resources effectively. So in this case, we have sensors that are smart, the smart water sensors from the reservoir to inform us that how much of water that was dispatched from the reservoir number one to reservoir number two up until it gets to the tanks, to the household, right? So these can help us to know, because we cannot run away from the fact that water can be leaked along the way. So we may not, if maybe the water that was dispatched can be maybe 100 liters, you find that by the time water reaches households, it's about 50 liters. So we want to make sure that we are able to see the process or the progress from the first reservoir to the tanks, so that we know how much of water resources we have, and then share it among the individuals. Even here, we can still make use of the Tswane Wi-Fi in terms of communication, and then also do the visualization to know, do we have enough water to distribute? That's where the decision-making comes in to say, yes, we can distribute, or no, we cannot distribute. So that is the context of resource sharing among the community. Now, in terms of research, these are the steps that needs to be followed for us to achieve this huge project. Number one, to make sure that we investigate the current existing decision-making approaches that are using the stream data or real-time IoT-enabled data. And among those existing approaches, then we identify the potential ones, and to make sure that we use the ones that can yield effective results. Then propose the optimal techniques that can be used to make sure that we take right decisions, given that data can be lost along the way, right? And then at the end of the day, after proposing and implementing that optimal technique, then we need to evaluate it to show that it really works, or it works better than other existing approaches. Now, because we are in the era of 4IR and other technologies that are enabled, so in this context, we decided to use the approach of machine learning, whereby machine learning can use labeled, the data set can use labeled, unlabeled, or both. But in this case of the waste collection use case, we are using the labeled data. So that leads us to a category of a supervised learning, right? And then the complexity of this data can be labeled or unlabeled, right? So because of that, it can, at the end of the day, our models will be around the classification. So it means that for waste collection, we're gonna look at the classification models and see which one can work better than other models that exist out there. So by labeled data, we mean that if, for example, we say if the bin can range from 0 to 30%, then we categorize it as empty. From 30% to 60, it's half. From 60 to 100, I'm just making an example. We know this, the half of 100 is 50, but I was just making an example. From 61 to 100, then it's full. So those are the kinds of labeled data that we are referring to. But for water distribution, in this case, the data is unlabeled because it's not a matter of we can give it a certain category. So because the data is unlabeled, it uses the unsupervised learning method, and still the data can be linear or non-linear. It can be continuous or categorical. And then at the end of the day, we use the models that are called clustering models, right? So this is the generic, almost generic decision-making model that we decided to use. So it means that we're gonna sense the data, and the data we wanna check if, because remember, before you utilize any classification model or clustering model, you need to train it, right? So if it's a streaming data, you can't train a model with a streaming data. You always need to have a data at rest. Remember that data that was in a red category, that is the data at rest, the data that can be stored in a certain device, even for over a year or even more, So we use that data to train a model. It means that a training can only happen with this initially, right? But as time goes on, because of the smartness of the model, it can learn and keep on updating itself, right? So now we train a model, and after that, we test the model with the streaming data. Data in motion is the streaming data. When we train this model, then we classify or we cluster that model using the trained model to make those decisions. I hope that is clear. right? So these are the classification models that we considered. Remember, one of the objectives is to identify the potential decision-making approaches that can be used. There is a long list of classification models, but based on what they do, we evaluated them theoretically, and we chose these ones to say these are the ones that are closer to what we want to achieve, but we still have to test them. So they were all tested, and we tested them with complete data to check how each behave at 10% of missing data, how each behave at 20%, at 30%, at 40%. So the numbers that you see on the screen are the numbers of the highest performance, highest accuracy. Now, we ended up at 40%. At 50%, we also tested it, but none of them were performing. They looked like they were just returning same values. So based on the observation, it was like, nah, this is bias now. So it means that our model was trained to take up to 40% of missing data. So it means that even if household number 2, 3, 4, 5 may have missing data, but we can still take a decision to say we are collecting in section A or not, right? Now, let's look at the clustering models for water now. This is not for waste collection. For water, we just looked at these 5 models, the logistic regression, LDA, and the K-neighboring classifier and all that. So let's see how was the performance. This was the performance for all these clustering models. So it means that the logistic regression was the one that was performing much better than the other clustering models, right? So in conclusion, this is what we are saying. We are saying, if ever there is a chance to be in a space or in any domain with connected sensors that can potentially generate data in a well-established communication, it means that we can be able to visualize, to see what is happening with those devices. And because we'll be informed, it means that we can make those decisions. We can also do a survey, or we can do a monitoring of those objects. So who is going to benefit out of the day? It's the environment, it's the people, it's better service, maybe for buildings, for cars, traffic, other services, and we can have an effective lifestyle. So it means that anyone, seeing this model can even think about agriculture, that, actually, we can even utilize the same model for agricultural purposes. We can utilize the same model for financial purposes. I remember Reserve Bank was also asking a question of what can we do with the Internet of Things? You can even manage the trucks coming in, going out, the exporting and importing. And because of that, you can be able to predict. It can even boost the prediction in the financial models to say, okay, will there be a recession? Should we expect this? Should we expect that? So because of this model, I believe that there are lots and lots of use cases that can potentially be utilized using the very same model. Thank you very much for your time and for listening.